Conversations That Matter is a partner program for the Center for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the support of the following and viewers like you.
Nathan Gilliland, welcome.
Thank you. Thanks for having me.
For most of the past 40 some odd years, we've had the promise of fusion.
Right.
It's been hanging there saying, come and get me.
Yes.
And it's fascinating that here in Burnaby, you are taking an approach that may get us over that finish line. Tell me a little bit of, first of all, let's define what fusion is versus fission.
Yes.
And why it's an energy production method that we really need to embrace.
Yes.
What the promise it brings with it.
Yes. So fusion is what happens in the sun. So the sun is a big ball of hydrogen that uses gravity to squash hydrogen together to make helium. And when that occurs, a huge amount of energy is released. We see it in the form of light and heat. The benefits of it, it's basically the ultimate carbon-free energy source, meaning, you know, and some people would call it the holy grail of renewable energy or clean energy. But the big benefits are that unlike fission, it has no possibility of a meltdown. There's very little safety risk. We're talking about very small amounts of hydrogen that are fused together, and the only things that are released are energy and helium.
There is a small touch of radiation, though, is there not?
There is a little bit of, it's like a hospital medical imaging facility where there's a lightly radioactive material after running a facility for many years, but it's a very different animal than, you know, having waste fuel rods and that kind of thing.
Because it dissipates quite quickly, does it?
It does. It does. There's as part of the fusion process, neutrons are emitted, and they can lightly activate material that's in the fusion reactor. But it's like I said, it's compared to it's like a hospital nuclear medicine facility. So it's not in the same class as fission. But the one more point I wanted to make. So I talked about safety and I talked about limited emissions. The other big and probably the biggest benefit is that you have an unlimited energy source. So you literally have billions of years of fuel on the Earth. It's the most abundant element in the universe, hydrogen. And being able to take that hydrogen and fuse it together, it sort of changes everything. It changes how we think about food security or water, because you can desalinate water. It really changes the way we think about energy and relate to energy, and that's probably the biggest.
It's my understanding that if you took a gallon of water and were able to make fusion happen the way that we envision it, that it will have the energy generating capacities of about 300 gallons of gasoline.
That is correct. That is correct. I often think about it in terms of, you know, kilograms of hydrogen. And so 1 kilogram of hydrogen has the equivalent amount of energy of 10 million kilograms of coal.
10 million?
10 million kilograms of coal. So it's incredibly energy dense. So, you know, when we think about our energy facility, the amount of hydrogen that we require in a year, you know, would fit, you know, comfortably, you know, right in here. It's a very small amount of hydrogen makes a huge amount of energy.
So as we've watched this process unfold, the biggest challenge was having the ability to create enough energy to ignite even more energy. And right now it's taking more energy to create the energy and so it's you know,
it's not
there's
quite
no gain
there.
yet.
Right.
So how do we overcome that barrier? Especially considering, you know, you take a look at the ITER project in France, and then the huge accelerator, I believe it is in Germany, and yet you're doing something that is like this in scale. How is that possible?
Yeah, I think you are correct. I think that the big step in fusion is to get more energy out of the reaction than you're putting in, and until that time happens on a repeatable basis, fusion's not there. The challenge is we have to get material and hydrogen up to tens of millions of degrees. That's the only way that fusion can occur. So it takes
100 million or more, isn't it?
It depends on the way you're doing it, but yes, 100 million degrees is a good number. The problem with that is it takes a lot of energy to create something at that temperature. So lots of energy has to go in. It doesn't matter what the fusion process is. It takes a lot of energy to go into the plasma. And I say plasma, that's just hot hydrogen, hot hydrogen gas. So, and then in terms of us versus ITER, there are a number of large government programs. Yes.
I just want to clarify. Plasma is one of the essential elements of the universe, is it not? Like, it's everywhere as well.
Yes.
So it's not like you're having to create the plasma out of something else. It's like all of the ingredients that go into this are natural sources.
That's exactly right.
Okay.
In fact, the sun is a big ball of plasma, and all the stars in the universe are big balls of plasma. So when you look at the night sky, you're seeing light emitted from plasma, essentially. So it is common. The tricky part is it's very hot, and it's a complicated material to work with. It's not a solid, it's not a gas, it's plasma. So
and
it's complicated.
It doesn't react in a straightforward action. So if you drive it this way, it could go that way.
That's right. That's right. So kind of going back to early days of chemistry, you've got a proton and an electron typically, and electrons flying around the proton. Well, in a plasma, the electron and the proton are separated from each other. So you're trying to fuse two protons together that it's two positively charged elements that are trying to fuse, and they don't want to fuse.
They do not want to fuse.
They're trying everything they can not to fuse. So this is the tricky part. So
what are the main components that will make it fuse?
Yes. So it is all about getting the temperature high enough so that the material, the hydrogen is moving fast enough, and that the heat, and secondly that you're containing the heat, because as it gets hotter and hotter, just like anything, it wants to expand and the heat wants to dissipate. So it's a combination of making the fusion happen and then holding that heat in long enough.
That brings up like a question that I go, okay, obviously you figured this out, but how do you have something that's going to reach 100 million degrees and contain it within anything that's man-made?
Yes.
And not have that vessel melt.
Yes, yes. That's a challenge as well, and different pathways to fusion try to do that in different ways. In our particular case, I think one way to think about it is, though it is extremely hot, it's a very small. It's about 4 centimeters of material, hydrogen, and that 4 centimeters.
That's it.
Yeah,
4 centimeters.
4 centimeters in diameter at the end of our process. Very hot, but surrounded by that is 4 meters in all sides of a liquid metal, a liquid lead, and that easily absorbs all the energy that's released from the reaction. I haven't described how our process works yet, but it's a little bit like if a match is a very hot thing, but if you threw it in a big bathtub, you wouldn't worry too much about the material and the water in the bathtub. But there are challenges in fusion with that superheated material, and whatever's next to it is also going to be vaporized as well. It's one of the big advantages and differences of the way we do it is that our wall around the plasma is actually a liquid metal. So it's a hot lead in our case that we're spinning in a vortex. Like if you took a drain out of a sink, you're creating a vortex. And so we've put a plasma in there and then smash that plasma together. So as all the fusion occurs, it just heats up that lead. So our liquid, if you think about a liquid wall, you can't kind of tear it apart. It's just a liquid. So it has a huge amount of benefits in terms of much easier to make power out of it, and certainly protects the reactor from some of the issues you were just mentioning.
I've got to get you to hang on for a second while
Sure.
we take a quick commercial break. We'll be right back.
Conversations That Matter is a not-for-profit program made possible thanks to the charitable support of the following and from viewers like you. Please visit conversationsthatmatter.tv and help us to continue to produce this program.
So let's talk about the unique way in which you are creating that fusion, especially if those particles are trying to avoid one another at all costs.
Right, yes.
What is it that you're doing?
How are we doing it? So I think that an important point to start with on there is that the history of fusion has been primarily focused on a couple of pathways. One is it's a type of plasma called a tokamak, which is a donut-shaped ball of plasma that has a bunch of electric current in it, and you just hold it together indefinitely and heat it up and let fusion happen. And that's research has progressed very nicely. On the other side, the idea is to take a little tiny ball of hydrogen and then smash it with lasers from all sides, and do that kind of every once in a while. So one you run continuously, one you kind of shoot every few seconds. And the problem with that is, the problem with those two is now the laser that's required to do that is the world's biggest laser. And the material that's required to do the tokamak is the world's biggest superconducting magnet. And what that means is they're incredibly expensive.
They're big.
They're huge. They're absolutely huge. And so the innovators in the space like us are trying to take the best of both of those and try to do this in a way that's a much simpler and doesn't require a lot of expensive materials. So getting to your point, we don't have any exotic materials. We don't have any superconducting magnets or lasers that are involved in our process. We simply create this plasma, and in our case, as I mentioned, we have a liquid metal circulating in a big ball, about 2 meters, in about 2 meters in diameter.
So there's a centrifugal force that's driving this around.
Correct. We're injecting this liquid lead, it's spinning around, and we're dropping a plasma in there. And then in our case, we have about 4-meter pistons, like car pistons, but much stronger, much faster. And all around this big ball are pistons. And from all sides.
So what's the point of having it from so many different directions?
The point is then when those pistons hit that liquid metal, there's a shock wave that's sent through that liquid metal and from all sides, and then just squashes that plasma that's in the middle.
So it doesn't allow it to escape away from the source of energy.
Exactly. It's literally from all sides. It's like a balloon that you're trying to squeeze from all sides. And so it needs to be fairly symmetrical, and in our case, we squeeze it from about 40 centimeters down to 4. And it needs to be quite symmetrical, and that's one of the challenges that we have.
So the piston comes down, and I was reading that it strikes an anvil, which then I guess drives energy into the liquid metal and then towards the plasma.
Yes, yes. It's a bit like a nail and taking a hammer and hitting the nail. So all that energy from your hammer is dumped into that nail when you hit it. It's the same idea. A piston fires at about, in our case, 65 meters a second, which is a lot, and hits an anvil, which puts all the energy into the anvil, which then puts its energy in the form of a shock wave into that liquid metal, which then compresses the plasma.
So it's not a direct point, it's a shock wave that comes out to help contain the energy?
Yeah, it's a shock wave that if you picture a sphere covered with pistons, covered with 200 pistons.
200?
200 pistons. Huge. It looks a little bit, I encourage you to come out sometime. It looks like something out of science fiction, I'll be honest. But it's got 200 pistons around it, and that when they hit, the shock wave focuses. So you're getting a convergent shock wave that comes in and then compresses that plasma, and as you said, keeps the energy in.
This is our second commercial break. We'll be back in a moment.
Conversations That Matter is a not-for-profit program made possible thanks to the charitable support of the following and from viewers like you. Please visit conversationsthatmatter.tv and help us to continue to produce this program.
So it then, when it creates that fusion, it's now creating the energy that's going to hopefully be able to transfer that back out into a commercial application.
Yes,
that's the long-term goal.
That's absolutely the goal. There's no question. And so what happens then? I described the process. The fusion reaction occurs. A huge amount of energy is released, and what happens is that lead that's surrounding the whole plasma, the fusion reaction, is heated up. So it's heated up a couple hundred degrees Celsius, pumped out, and then we make steam to make electricity, just similar to any of the traditional ways that steam turbines work.
When you say a couple hundred degrees, does the temperature from the fusion actually dissipate that quickly within the liquid metal to get down to just a couple hundred degrees Celsius?
It does. It does. The temperature at the at closest is hotter than further away, but it does dissipate because remember it's also circulating during the whole process. So. And we will fire it about once per second. So in a way that think about that lead as being continuously pumped in and out, heated up, cooled down by the steam that makes electricity.
When you say once per second, are you saying the firing off of all pistons is going to happen within 1 second?
Yes, once per second. So it's sort of boom, boom, boom. I will say we're not there yet. We're not there yet. I think we're the next generation prototype we expect to fire a couple times a day. And the goal there is to demonstrate repeatable fusion reactions that are approaching break even or possibly net gain. But we're certainly not there yet in terms of firing once per second.
Okay.
That's the goal. That's certainly the goal.
Firing once per day, how much energy would that produce if you're only firing once a day?
Yeah. It's not. Think of it. That plant is not necessarily a commercial plant yet. It's there to better understand reliability of these pistons that I talked about. A lot of the smaller engineering challenges of pumps and valves, and as I said, reliability. So the plant after that one would be, if things go well, that would be the one that I think could put electricity on the grid. But you see, we're a few steps away from that still.
I'll come back to where we were at, but
Yeah.
I'm fascinated by the idea of, well, how often would you have to be firing to start to be able to produce a commercially viable amount of energy?
Yes.
Which gives us an idea of how far we have to go from where we're at right now.
In reality, once every few seconds is the place we have to get to create significantly more energy out than we're putting in. So think about 100 megawatts of energy is coming in to produce about 600 megawatts coming out of the reaction.
So that's a good return on investment.
That's a good return on investment. That does assume firing once per second. I think, though, that let's not get too caught up or concerned about the rate of firing, because think about a car and how fast those pistons fire, many times per second. So that challenge, I think, we haven't solved it yet, but I don't look at that as one of our most difficult ones. I think the most difficult challenges have to do with, as you compress that plasma, how far can you compress it before the heat escapes? Can you really contain that energy long enough to get to the energy gain that's required? That's the hard part. That's the piece that we're still working aggressively on.
Who knew that fusion could be so interesting? But I don't want to keep going, but I got to take one last break.
Yeah.
We'll be back in a moment.
Conversations That Matter is a not-for-profit program made possible thanks to the charitable support of the following and from viewers like you. Please visit conversationsthatmatter.tv and help us to continue to produce this program.
Because we're experimenting, when you project, what do you think it's going to take time-wise and to overcome some of the challenges or obstacles that you currently face, to be able to say, there it is, the model works, now we go to the next stage?
Yes. I think a couple thoughts there. One is we can look back at history, and as we talked about at the beginning, and how much progress has been made in the past. I think that's an important benchmark to suggest where things will head in the future as an industry. So between 1970 and the early 2000s, the amount of fusion energy we're getting is about 30,000 times more per reaction than we were getting back in 1970. So it actually followed Moore's law, the law related to the number of semiconductors, your chips, circuits you can put on a chip. It's followed Moore's law for most of that time. So it's come a long way, which gives us a lot of hope about where things are headed. The second thing that gives us hope is the number of fusion programs that are in development now. It's a kind of a golden age of private fusion companies now, with six private fusion companies getting funding last year, real funding, over $10 million, including us. So all of those.
And part of your competition is MIT as well, isn't it? Yeah.
Yes, they're competitors, but they're collaborators too. As an industry, we're not yet fighting with each other, and sort of. We're actually doing quite the opposite. We hold workshops to bring in people from other companies like that. Like one of the other large fusion programs is called Tri-Alpha down in Los Angeles. We regularly have them up and talk about some of our challenges and vice versa. There's a lot of information sharing that occurs. MIT's and Princeton, we have a partnership with Princeton where they're doing work for us. So we're still collaborating. I think there could be some point in the future where that changes. But to get back to your question about the timeline, I'm not totally
close are
avoiding
we?
it. I'm not totally avoiding it. So there's a lot of feels like there's a lot of momentum right now, and I would add to that. I think the humanity is not afraid to go after some of these really hard challenges now in a different way than maybe 20 years ago.
Yeah.
When we look at robotics or artificial intelligence or big data or self-driving cars or trying to fly to Mars with a private company. I mean, the fear of going after some of these really hard challenges is dissipated. So that's another factor. But in terms of us and I think the industry, we still have a little ways to go. There's no question about it. So in our case, we need to prove out that our concept can get to more energy out than in. That's net gain, we call it. And we're doing that on an experimental basis. We run experiments every 15 minutes at our facilities in Burnaby. So constantly. And our hope is that we can prove that out in 2 or 3 years. That's if things go well. At that point, we'd build a pre-commercial prototype that will demonstrate this on a repeatable basis. And then following that, we could build commercial plants. So, adding that all up, it's still, it's not 3 years away or 5 years away.
More like 20.
I hope it's faster than that.
Yeah. But I was listening to an interview with, is it Mr. Digo from the ITER project, and he said, to be realistic about when we will start to see it enter into the commercial environment, probably the latter half of this century. We'll have proved it before, but then you still need to build out the facilities and make this happen. And so it is a energy source of the future, but if it works, could be a fantastic source.
Yeah, it changes everything, and I think Mr. Rigaud from ITER, who's a friend of ours, I think he's correct. Their pathway is the one that I talked about the superconducting magnets.
Yes.
It's also a multi-government bureaucracy. It's 9 governments trying to build the world's most complicated science experiment. So they're understandably on a slower timeline.
Yeah.
As a private company, us and I think the other private companies would all tell you that our timelines are much, much shorter than that one.
Yeah.
No question about it. And, we may hit physical barriers that prohibit us from getting there, but for us, it's all about practicality and a focus on commercialization. That's the goal. I think ITER, as you mentioned, is more about science and basic research. There's nothing wrong with that. We are all benefiting from that, but it's not meant to be, a clear pathway to commercial fusion.
So I had Professor Tim Flannery, who had been the climate commissioner in Australia and wrote Atmosphere of Change and Climate of Hope, and he said that our number one producer of greenhouse gases is the burning of coal to produce electricity.
Yes.
And for all who are concerned about the volume of greenhouse gas in our atmosphere, we're rooting for you because this is a game changer.
Yes.
Yeah.
Yes. Thank you. Thank you.
Thank you very much. Thanks for coming in.
Yes, you're welcome. You're welcome. Thank you.